have you ever stopped to think about how your phone can translate languages almost instantly? Or how a chatbot actually understands what you're asking? Well, it's not magic, that's for sure. It all comes down to teaching a computer how to read. And, the very first lesson is always the same: how to clean up the incredible, beautiful mess that is human language.
See, for a machine, our words are just chaos. They're raw, unstructured data. It's not like code, right? Our language is full of nuance, slang, and ambiguity. So before a computer can even begin to find any meaning, we have to be the ones to create order from that chaos.
And that's exactly where text preprocessing comes in. Think of it as our toolkit. It's this whole set of techniques we use to turn that messy text into a clean, structured format that a machine can actually work with. It's kind of like a chef doing all the prep work, chopping the vegetables, measuring the spices before they even start cooking. It is the absolute foundation for everything in natural language processing, or NLP.
So where do we even begin with this cleanup? Well, the very first step is to take this huge wall of text and, break it down into manageable little bricks. This is a process called tokenization. It's a bit of a fancy word, but all it means is that we're splitting up a document into smaller pieces, or tokens. These are usually just words or sentences. This is step one, the ground floor in helping a machine see the basic building blocks of our language. Let's actually see how this works. Here's a bit of code. We're giving it two simple sentences as input. Cats are running faster than ever. They are amazing creatures. And we're asking the computer to tokenize this text, splitting it up by both words and by sentences.
And boom, here's what we get back. The machine doesn't see a paragraph anymore. It sees a nice, neat, ordered list of individual words, and below that, a list of two completely separate sentences. The text is totally deconstructed and organized. The first step is done.
Okay, so we've got our words, but this brings up a new problem, right? The words run, running, and runs, to us, they're all basically the same concept. But to a computer, they're three totally different strings of characters. So how do we get a machine to get that connection? Well, one way is a fast, kind of rough method called stemming. Stemming is a little bit like a linguistic lawnmower. Seriously, it just uses a set of rules to crudely chop off the ends of words, the prefixes and suffixes, to try and get down to a common root, or a stem. It's super fast, which is great, but as you're about to see, it's not always very precise.
All right, so here we're using a classic stemming algorithm. It's called the Porter stemmer, and we're going to feed it a list of words with different variations, words like running and runs, but also some adverbs like easily and fairly.
Now look at the output here. For running and runs, it works perfectly. They both become run. Awesome. But then look at easily and fairly. They get chopped down to easily and fairly, which, are not real words. This really shows you both the power and the, let's say, crudeness of stemming. It gets the job done, but it's not pretty. And this brings us to a really important point. There isn't just one way to stem. There are different types of stemmers out there. The Porter stemmer we just used is one of the originals, but it's been improved upon. So let's take a look at its more modern successor, the snowball stemmer.
Okay, check this out. On the left, you've got the results from the old-school Porter stemmer. On the right, the results from snowball. Now, for most of these words, they look identical. But look closely at a tricky word like denationalization. Porter shortens it to denational, but snowball actually takes it one step further, down to denation. It's a subtle difference, but these little things can really matter.
So, what's the big difference? Well, the original Porter stemmer is really just for English, and it's not very flexible. Snowball, on the other hand, is not only faster and often more accurate, but it also supports a bunch of different languages. That makes it a much better choice for most of what we do today. So, stemming is great when you need speed. But what if you need accuracy? What if it's absolutely crucial that the root word you end up with is a real, actual dictionary word? For that, we need a smarter tool. And that smarter tool is called lemmatization. Now, instead of just blindly chopping off the ends of words, lemmatization is much more sophisticated. It actually uses a dictionary to find the true base form of a word. It's lemma. This is way more about linguistic analysis than just following some crude rules. So let's put them head to head. Stemming is the fast, simple, rule-based chopper. It's the brawn. The output might be nonsense. Lemmatization, though, is like the dictionary-wielding linguist. It's the brains. It's a bit slower because it's actually thinking about the word's context, but its output is always a valid word. And here is the payoff. Plain and simple. Remember how our stemmer turned easily into the nonsense word easily?
Well, look at what lemmatization does. It correctly identifies that the base form is, in fact, easily. It knows it's a real word, so it keeps the meaning completely intact. That's a huge difference.
Okay, let's take a breath. We've broken our text into pieces, we've normalized the words, but why? Why did we go through all this trouble? Let's connect these crucial steps to what all this amazing NLP tech can actually do.
What we've really done is build a text cleanup pipeline. Step 1, we tokenize the text to break it down into chunks. Step 2, we normalize those chunks using either stemming or lemmatization to group different forms of the same word together. And now, for the final step, this clean, beautiful, structured data is ready to be fed into a powerful machine learning model for some real analysis.
And why does all this matter? Because this fundamental cleanup process is what makes everything else possible. I'm talking about sentiment analysis that can tell if a product review is positive or negative. I'm talking about the chatbots and virtual assistants we use every single day. Machine translation, speech recognition, all of it, every single one, is built on this foundation of clean, pre-processed text.
So, we've done it. We've successfully cleaned and organized our words. The machine can count them, it can see their root forms, but this leads us to the next really fascinating challenge. The words themselves are clean, but how on earth does a machine understand what they actually mean when they're sitting next to each other in a sentence? Now that is a topic for our next explainer.